Okay, so previously we were introduced to the continuous spectrum that you can get from white light or some white light source. So now we're going to look at line spectrum for different elements and how that is related to the electronic arrangement of atoms in the particular element. So what we have here, what you're looking at here on the screen here is what you call a hydrogen lamp, which is basically a tube which consists of hydrogen inside the tube in at low pressure, I should say. And each end of the tube has electrodes which are connected to an electric circuit, which is not shown. All right. So when the switch is flipped, what happens or what is observed is that the hydrogen in the lamp glows, it produces light. And if that light is projected through a slit and then passes through a prism, which is projected eventually onto a screen, you're going to end up with what is known as a line spectrum, all right? Which is different from the continuous spectrum, because in the case of a line spectrum, when you look at the line spectrum that is formed as a result of projecting the light onto the screen, you will not see different colors of light running into each other as you go from one end to the next. Instead, what you'll observe are specific lines which will have specific colors. So I don't know if you can see the different colors here, but I see something looking like a red or pink line right here. I see a blue line right here. And these two lines here, they look either purple or violet, whichever, or indigo, whichever color you can see there. All right, so that's what happens in the case of hydrogen. And if you use other lamps with different elements, again, under the same conditions of low pressure, then you're going to get different line spectra for different elements, all right? In fact, what you're looking at here on this slide are different line spectra for different elements, for mercury, for lithium, for cadmium, for strontium, all right? And what you'll find is that each element has their own unique pattern of lines. In other words, each element has their own unique line spectrum. So we can actually use the line spectrum to identify elements. In fact, this is what is used to identify certain elements that exist in the sun. Astronomers have their special instruments that they use to analyze the light coming from the sun. And based on the line spectra that they could obtain, they can identify certain elements that exist up there as gases that would exist as, solids down here. For example, iron is a gas up there in the sun. All right. And they know that because they can identify the line spectrum of iron based on the radiation that is emitted by the sun. All right. So that's basically the line spectra that is produced by elements under the conditions that I just described. Now, how does this help us in terms of determining the electronic configuration of an atom? Well, before we get to that, let's talk about quantum theory, and in particular black body radiation, which ultimately leads to our current understanding of the electron arrangement. So this guy Planck, he proposed that when you have atoms that are vibrating in a heated solid, they will absorb or emit electromagnetic radiation in only discrete amounts. And the smallest amount of energy is called a quantum, and its energy is given by this equation. E is the energy of the quantum, is equal to h, which is known as Planck's constant, multiplied by the frequency of the radiation, which would be in hertz, right? So basically what Planck is saying is that for any solid that is heated, and as a result of being heated, the atoms will be vibrating, then they will absorb or emit energy equal to a quantum, which is given by this expression, all right? And therefore, he came up with this hypothesis which states that the energy can only be emitted or absorbed as either a quantum or an integral multiple of a quantum. So, meaning that you multiply whatever the quantum value here by some integer. And that would represent the amount of energy that is absorbed or emitted by an atom or by a particular substance which is heated. Okay, so that's basically what Planck proposed as a hypothesis. And then Einstein, he came up with something which is related, because what Planck is suggesting is that the energy of a substance is changed by either a quantum or multiple numbers of a quantum of energy. So what Einstein came up with is this notion that electromagnetic energy can exist as small particles known as photons. And the energy of the photon is equal to the same equation that Planck proposed. So therefore, basically what this seems to suggest is that when a substance loses energy, it loses photons, and the photons carry an energy equal to this expression, E is equal to h nu. So to examine this particular idea further, this experiment was set up. Now, I'll be honest with you, I don't remember who set this experiment up, and me probably need to look this up and include this in a later video. But basically, what happens here is that you have an anode, which is connected to an electrical circuit, and as a part of this circuit, you have what is known as an ammeter. An ammeter is basically an instrument that is used to indicate and measure an electric current flowing through the external circuit. Now, we also have another electrode here, but this electrode is made up of a material which is said to be photoemissive. So what that means basically is that it will easily give up electrons or lose electrons when exposed to radiation, and in particular light of a particular frequency. So that serves a role as the cathode. And the electrodes, the anode and the cathode, are basically encased in this glass casing right here, which allows for the incoming radiation to hit the photoemissive cathode. And as I said before, the radiation will basically knock off electrons from the cathode, and the electron will actually travel through space from the cathode to the anode. As a result of that migration of electrons, there will be an external current flowing through here, which will be detected by the ammeter here. All right. So what was discovered while this experiment was being done was that the, how should I put this now? The current will not flow unless the frequency of the radiation is above or at a certain threshold value, right? So basically, if the frequency is below a certain value, then no electric current will flow through, right? Once you get to that particular frequency, then all of a sudden, you're going to see an electric current detected, right? So basically what this says is that the flow of electric current is dependent on the frequency of the radiation that the photoemissive electrode is exposed to. Another thing that was noticed was that the flow of the current is independent of the photon intensity. In other words, the flow of the current is not in any way dependent on how bright the radiation is. The brightness is basically related to the photon intensity, the number of photons that are present. So basically we can conclude that the current flow is not dependent on the number of photons, but as I said before, dependent on the frequency of the radiation that the photoemissive electrode, the cathode, is exposed to. All right. Okay. So, so that's basically what I'm going to talk about here. And oh, by the way, this is called the photoelectric effect. All right. Okay. So that's it for this particular section. The next video I'm going to post, I'm going to try to tie what we just discussed to the Bohr model of the hydrogen atom. All right. And then go from there. All right. Okay. Until next time.